Welcome back. It's time to tackle implication world. We've proved that 2 plus 2 equals 4. In implication world, we'll learn how to prove that 2 plus 2 does not equal 5. In addition world, we prove equalities like x plus y equals y plus x. In this second tutorial world, we'll learn some new tactics enabling us to prove implications like x plus 1 equals 4, therefore x equals 3, I guess. We'll also learn 2 new fundamental facts about natural numbers, which Peano introduced as axioms. So we're going to get to the Peano axioms. Click Start to proceed. Okay, in this world, we'll learn how to prove theorems of the form P, therefore Q. In other words, how to prove theorems of the form if P is true, then Q is true. To do that, we need to learn some more tactics. The exact tactic can be used to close a goal which is exactly one hypothesis. It takes the name of the hypothesis as argument, exact H. The goal of this level is one of our hypotheses. Hypotheses. Solve the goal by excluding solve the goal by executing exact H1. So tactics, we have exact. So x plus y equals 37. And we have our hypothesis 1, which says x plus y equals 37. We also have a second hypothesis that says 3 times x plus z equals 42. But all we have to do is exact H1. I wonder what the other hypothesis was there for. Wait, assuming x plus y equals 37 and 3x plus z equals 42, we have x plus y equals 37. I don't understand why this second hypothesis needs to be here, I guess. But I guess that's that one. If the goal is not exactly a hypothesis, we can sometimes use rewrites to fix things up. You can use rewrite 0 add at h to rewrite h instead of at the goal. To rewrite at h instead of at the goal. Okay. So our hypothesis now is 0 plus x equals 0 plus y plus 2. So we just have to get rid of our zeros. So like it says, we'll rewrite 0 add. But we want to rewrite our hypothesis. There we go. Now we can just now you could finish this with rewrite h, then reflect, but exact h does it in one line. Okay, so we can just, I see. Okay, cool. Here's a 2-line proof. Repeat. Oh, that's the one I did. Nice. Nice. In this level, the hypothesis H2 is an implication. It says that if x equals 37, then y equals 42. We can use this hypothesis with the apply tactic. Oh, we get a new tactic. Remember, you can click on apply or any other tactic on the right to see a detailed explanation of what it does, with examples. Start with apply H2 at H1. This will change H1 to y equals 42. So this is our implication. If x equals 37, then y equals 42. So if I say apply H2, right now it's just applying it to our goal. So the original goal was y equals 42, and then we applied H2, which changed it to x equals 37, but we want to apply it to our first hypothesis. So we turned the x equals 37 into y equals 42. They also switched places, which is kind of confusing. If the goal is a statement of P, then exact H will close the goal if H is a proof of P. So H1 says that y equals 42, and our goal is to prove that y equals 42. So we just used our hypothesis, which says, yes, correct, that is true. Okay, if A and B are numbers, then successor INJ, AB, is a proof that the successor of A equals the successor of B implies A equals B. Click on this theorem in the Piano tab for more information. Successor INJ. Piano had this theorem as an axiom, but in algorithm world, we will show how to prove it in Lean. Right now, let's just assume it, and let's prove that x plus 1 equals 4 implies x equals 3. Using it. Again, we will proceed by manipulating our hypotheses until it becomes the goal. I will walk you through this level. Let's first get h into the form successor x equals successor 3. So right now it's x plus 1 equals 4. And the successor of x equals the successor of 3. So we can apply the successor INJ. First execute the rewrite. 4 equals successor of 3. Add h to change the 4 on the right hand side. Okay, I think I get this. We can also, let me look for it. it wants me to do the 4 first, but I could also say x anything plus 1 I can use this one backwards. Rewrite backwards arrow successor equals add 1. No, that doesn't work. But it's n plus 1 should become the successor of n. And right here we have x plus 1, n plus 1. The successor of n equals n plus 1. And if I run that backwards using this arrow, then it should do it backwards. N plus 1 is the successor of n, and that should become the successor. All right, we'll just do it the way it says. We'll start with 4. Rewrite 4 equals the successor of 3. Wait. At h, I have to add at h. That's what I missed. Silly me. You can put an arrow in front of any theorem to provide a rewrite, in front of any theorem provided to rewrite the other way around. Look at the docs for rewrite for an explanation. Type backwards arrow with /1. Yeah, so I was on the right track. I just forgot to say at h, because we're changing the hypothesis, not the goal. Add 1 at h. I want to do it backwards. And now the successor of x equals the successor of 3. Okay. Now let's apply our new theorem. Execute apply successor ij. I wonder if ij stands for like integer. At h to change h to a proof of x equals 3. So we're going to use our first Peano axiom. If a and b are numbers, then this of ab is the proof that the successor of a equals the successor of b implies a is equal to b. Okay. Oh, I have to apply it. I have to apply it to h. And now all we have to do is, so I can either rewrite h, and now that changes it to 3 equals 3, or I could add a backwards arrow, and that changes it to x equals x, and I can use reflect. Or I can use the exact tactic. There we go. In the next level, we'll do the same proof, but backwards. In the last level, we manipulated the hypothesis x plus 1 equals 4 until it became the goal x equals 3. In this level, we'll manipulate the goal until it becomes our hypothesis, in this level, we'll manipulate the goal until it becomes our hypothesis. In other words, we will argue backwards. The apply tactic can do this too. Again, I will walk you through this one, assuming you're in command line mode, which I think I'm not. No, I am in command line mode and not in typewriter mode. Start with apply successor ij. I'm just going to call it successor integer. To apply successor integer to the goal. No, I don't think it is integer. It's like, what could it be, like injunction or something? Unless, is it obvious? Is it something? The proof that the successor of A equals the successor of B implies that A equals B. There are other ways to think about successor ij. You can think about successor ij itself as a function which takes two numbers, A and B, as inputs and outputs a proof that the successor of A equals the successor of B implies that A equals B. You can think of the successor ing itself as a proof. It is the proof that the successor is an injective function. Oh, that's it. Injective. Successor injective. That's what it is. In other words, successor injective is a proof of, I don't know these symbols yet. I know they're like logic letters. Anyway, let's just do what it says. Apply successor ing. Ing. So what did that do? That changed x equals 3 to the successor of x equals the successor of 3. Yep. Applying a proof of P implies Q to the goal changes Q to P. Now try to rewrite successor equals add 1 to make the goal look more like the hypothesis. Right? Okay. Now I guess I could use a backwards version of 4 equals successor of 3, or I could repeat this and then just add them together. Wait, no, I can't do that. You can't. Right? Can I? I don't think I can do that. I'm actually better off going rewrite backwards arrow 4 equals successor of 3. There it is. Then we exact H. No? X plus 1 equals 4. X plus 1 equals 4. Do I apply? I think that's... No? What am I doing? No, it is exact h. Oh, did I? I tried to put it in parentheses, or brackets. No brackets. Many people find apply t at h easy, but some find apply t confusing. If you find it confusing, then just argue forwards. You can read more about the apply tactics in its documentation, which you can view by clicking on the tactic in the lists on the right. Okay, what's next? We have seen how to apply theorem. We have seen how to apply theorems and assumptions of the form P implies Q. But what if our goal is of the form P implies Q? What if our goal is of the form P implies Q? To prove this goal, we need to know how to say, let's assume P and deduce Q. In Lean, we do this with the intro tactic. Intro. Start with intro H to assume the hypothesis and call its proof H. So if the goal is P implies Q, then intro H will introduce H implies P as a hypothesis, or it will introduce the hypothesis P as a hypothesis, and change the goal to Q. Mathematically, it says that to prove P implies Q, we can assume P and then prove Q. Okay. If your goal is x plus 1 equals y plus 1, therefore x equals y, the way Lean writes x plus 1 equals y plus 1 implies x equals y, then intro H will give you a hypothesis x plus 1 equals x y plus 1 named H, and the goal will change to x plus... Okay. Intro H. So the goal was x equals 37. Oh wait, so we started with no hypotheses. Just a goal that x equals 37, therefore x equals 37. And so we turned that into a hypothesis, and now we can use the hypothesis to prove okay. Let's see if you can use the tactics we've learned to prove x plus 1 equals y plus 1, therefore x equals y. Try this one by yourself. If you need help, click on the Show More Help. That's very similar to this. Okay. Intro H, x plus Gotta go get add one. Use this one backwards. Just like that. It won't let me. Oh, at H. There we go. And let's repeat it. Then we can use this one. I have to rewrite to use this, right? Rewrite successor injective at H. Nope, it doesn't like that. I feel like we probably use this one, but I've forgotten how I actually write it. Do I just write it? Is it rewrite? That doesn't work. I have to apply it. Okay. Apply. There it goes. Okay, I just forgot how I'm supposed to write it out. You have to apply it. It's not a rewrite, it's applied, which is different. We use apply for anyway. Now we can just, or is it apply H or exact H? I'm kind of struggling to understand the difference between apply and exact. If the goal is the statement P, then exact H will close the goal if H is a proof of P. Okay, it's exact H. There we go. Here's a completely backwards proof. Intro H, apply injective, repeat, rewrite, successor add one, exact H. That's almost like ours. Okay. We still can't prove that 2 plus 2 doesn't equal 5, because we have not talked about the definition of does not equal in Lean. In Lean, a does not equal, or in Lean, A does not equal B is notation for A equals B implies false. Here false is a generic false proposition, and false is a generic false proposition, and therefore is Lean, and this arrow is Lean's notation for implies. In logic, we learn that true implies false is false, but false implies false is true. Hence, x equals false is the logical opposite of x. Okay, that kind of makes sense. Even though A does not equal B does not look like an implication, you should treat it as an implication. The next two levels will show you how. False is a goal which you cannot deduce from a consistent set of assumptions. So if your goal is false, then you had better hope that your hypotheses are contradictory, which they are in this level. Remember that H2 is proof that x equals y implies false. Try applying H2 either at H1 or directly to the goal. So this is x equals y implies false. And this is x equals y implies true. And the goal is false. Does not imply. So just apply H2? I'm not sure I know what I did. Remember, x does not equal y is notation for x equals y, therefore implies false. So I applied H2, which turned the goal into x equals y. And then I used H1 to prove that that was true. Yeah, I'm not... I don't fully comprehend what I did there. As a warm-up for 2 plus 2 does not equal 5, let's prove that 0 does not equal 1. To do this, we need to introduce Peano's last axiom. 0 NE successor, 0 next successor. A proof that 0 does not equal the successor of n. To learn about this result, click on the list of lemmas on the right. Start with intro H. Alright, 0 next successor n is the proof that 0 does not equal the successor of n. In Lean, A does not equal B is defined to mean A equals B implies false. Hence, 0 next I don't know what the NE stands for. Successor n is really a proof that 0 equals the successor of n implies false. Here, false is a generic false statement. This means that you can apply 0 NE successor at h if h is a proof of 0 equals successor n. Okay, start with intro h. So 0 does not equal 1, and we turn that into a hypothesis that 0 equals 1 and that our goal is false. Now change 1 into the successor of h. Now change 1 to the successor of 0 in h. Just rewrite. At h. Now you can apply 0. Now you can apply this one to prove that 0 does not equal the successor of a number. 0 is not a successor of any number. Oh, we have to apply it. At h. And our hypothesis is false and our goal is false. So we should just be able to exact h. Okay. We know 0 any successor n is the proof that of 0 equals the successor of n implies false. But what if we have a hypothesis successor of n equals 0? It's the wrong way around. The symmetry tactic changes a goal x equals y to y equals x. And the goal of x does not equal y to y does not equal x. And symmetry at h does the same for a hypothesis h. We've proved 0 does not equal 1 and called the proof 0 NE1. Oh, this one here. Now try proving 1 does not equal 0. So all we have to do is symmetry. And that. No, we have to apply it. Apply 0. What do you think of this two-liner? That's what I did. Exact doesn't just take hypotheses. It will eat any proof which exists in the system. Okay. So now for the final goal, 2 plus 2 does not equal 5 is boring to prove in full, given only the tools we have currently. To make it a bit less painful, I have unfolded all the numerals for you. See if you can use 0, any successor, and successor injective to prove this. Okay, so the successor of 0, which is 2, plus the successor of 0, does not equal the successor of 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 0, which is 5. Intro H. We want them unfolded, because otherwise he wouldn't have unfolded them for us. So why do we want them unfolded? I'm not sure I know. What are we trying to do? The program has been helping me along so far, and as soon as it stops giving me help, I'm just like entirely lost. I have no idea how to do this. I have no idea what to do next. What do I have? See if you can use this one. What does this one do again? Is the proof that 0 does not equal the successor of n. 0 is not a successor. And successor injective, which is the proof that the successor of A equals the successor of B, implies that A equals B. Okay. I don't know. I'm feeling pretty brain dead today. Zero does not equal the successor of n. I don't know what to do. What did that do? Added a just added brackets. No, I think that was the first right step. Because now we need to prove that that's false or something. To be honest, I'm not sure I understood most of this world, most of this set of levels. I don't think I've understood most of Implication World. It helps you along so much that I was able to just follow along, but I did not really understand anything that it was telling me, and now we're here. What do I do? Is the proof that 0 does not equal the successor of... What happens if I just type that in? Does that even do anything? At H. No, that didn't. It failed to find the successor of 0 plus the successor of 0 equals... But this did something? Wait, what happens if I... No. Zero equals the successor of question mark A. Yeah, I don't think that's anything I want. No. No. It's the proof that 0 does not equal the successor of n. So this is just the proof that 0 is not the successor of any number. This is the proof that the successor of A equals the successor of B implies that A equals B. No, that doesn't work. I really don't know what to do. I'm just going to keep staring at it until the answer pops into my head. What can I do? Oh, I forgot at H. Okay. We did something. We got rid of the plus sign. That's what we did. Okay. It's the proof that 0 does not equal the successor of n. I could fold them back up and say 4 equals 5. that's not something we have. We need to say that 0 is not the successor of n, and that the successor of A equals the successor of B implies A plus B. It implies A equals B. So the successor of the successor of the successor of the successor of 0 equals the successor of 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 0. 4 equals 5, and I need to prove that that's not true. I mean, can I just... No, that doesn't work. Wait, that worked? That did something. Successor ij proves that the successor of A equals... Oh. Can I repeat this? There it is. Okay. I just repeated that over and over again. So the successor of 0 equals the successor of 0 becomes 0 equals 0. And then you just keep repeating that down the list until you end up with 0 equals the successor of 0, which we can prove is not true using this. And false equals false. Exactly. Yay! Here's my proof. Intro H, rewrite, add successor, add 0 at H. Oh, okay, I wrote that a little differently, but it's the same thing. He wrote it in one line. They wrote it in one line. Then repeat, apply successor in H, which is what I did. Nice, okay. Even though Lean is a theorem prover, right now it's pretty clear that we have not developed enough material to make it an adequate calculator. In algorithm world, a more computer sciencey world, we will develop machinery which makes questions like this much easier, and goals like 20 plus 20 does not equal 41 feasible. Alternatively, you can do more mathematics in advanced addition world, where we will prove lemmas needed to get a working theory of inequalities. Click Leave World and decide your route. Okay. Advanced Addition World or Algorithm World. Let's do Algorithm World next. That sounds interesting. Alright. Proofs like 2 plus 2 equals 4 and A plus B plus C plus D plus E equals E plus D plus C plus B plus A are very tedious to do by hand. In Algorithm World, we will learn how to get the computer to do them for us. Click on Start to proceed. Alright, A plus B plus c equals b plus a plus c. Having to rearrange variables manually using commutativity and associativity is very tedious. We start by reminding you of this. Add left commutative is a key component in the first algorithm, which we'll explain, but we need to prove it manually. Remember, you can do precision commutativity rewriting with things like rewrite, add, commutativity BC, and remember that a plus b plus c means a plus b plus c. Okay. So we have add right commutativity, but now we're going to prove add left commutativity, which is going to be the opposite of this. If a plus b plus c that doesn't work. Oh, there we go. I use it backwards to get rid of the parentheses. Then we just Oh, wait, that did it. Thought I was going to have to specify which ones I wanted moved around, but it just did it immediately. There we go. All right. In some later worlds, we're going to see some much nastier levels, like a plus 1 equals, a plus 1 plus b plus 1 equals a plus b plus 1 plus a plus b plus 1. Brackets need to be moved around and variables need to be swapped. In this level, a plus b plus c plus d equals a plus c plus d plus b. Let's forget about the brackets and just think about the other variable order. And just think about the variable order. To turn a plus b plus c plus d into a plus c plus d plus b, we need to swap b and c, and then swap d and b. But this is easier than you think with add left commutative. Start with repeat, rewrite, add associative to push all the brackets to the right. It's really just telling me what to do. Okay, that pushes all the brackets to the right. Now we use rewrite, add left commutative BC to switch B and C. Okay. Yep, and that switched the B and the C. And then we just add commutative to switch the B and the D. Now we have C plus B plus D plus A. Wait, that's not what that did. Oh no, use a targeted add commutative. Okay, there it goes. So that's the algorithm. Now let's use automation to perform it automatically. Okay. Whew. That's a lot of letters. It's too many letters. Lean's simplifier, simp, is rewrite on steroids. It will rewrite every lemma tagged with simp, simplify, and every lemma fed to it by the user as much as it can. This level is not a level which you want to solve by hand. Get the simplifier to solve it for you. Solve this level in one line with simp only. Okay, that's a new tactic, simp. We'll rewrite every lemma tagged with simp, and every lemma fed to it by the user as much as it can. Furthermore, it will attempt to order variables into simp only? Is that it? It's got this only in the same font as the other thing. It's made no progress. What are we trying to prove? We're trying to prove that D plus F plus H plus A plus C plus G plus E plus B equals A plus B plus C plus D plus E plus F plus G plus H. Okay. Yeah. Add left. Oh, okay. It's just, I'm overthinking it. I literally just type in what it tells me to type in. Add left commutative, and that gets all the brackets on the right. I know I just proved add left commutative, but I've already forgotten what it does. Is the proof that A plus B plus C equals B plus A plus C? It seems like such an... Oh, it's the B that's on the left. And then in this one, A plus B plus C equals A plus C plus B. And that takes the one on the right. So this one, it takes this letter on the left of the two and puts it first. So it takes this G plus E and puts it first. But it leaves this B. Now let's make our own tactic to do this. We're going to make our own tactic. You can make your own tactics in Lean. This code here. Macro simp add tactic simp only blah 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 was used to create a new tactic simp add, which runs simp only add associative, add left commutative, add commutative. Okay, so it made it for us, but when we're actually using Lean later on, when I get the actual program and start learning that, then this is the code that I'll use to make my own tactics. Try using it to solve this level. Oh, yeah, that's it. Now let's move on to a more efficient approach to questions involving numerals, such as 20 plus 20 equals 40. We now start work on an algorithm to do addition more efficiently. Recall that we defined addition by recursion, saying what it did on 0 and successors. It is an axiom of Lean that recursion is a valid way to define functions from types such as the naturals. Let's define a new function, predecessor, from the naturals to the naturals, which attempts to subtract 1 from the input. The definition is this. Predecessor of 0, predecessor 0 is 37. Predecessor of the successor of n is n. We cannot subtract 1 from 0, so we just return a junk value, as well as this definition. We also create a new lemma, predecessor-successor, which says that predecessor of the successor n equals n. Let's use this lemma to prove the successor injective, the theorem which Peano assumed as an axiom, and which we have already used extensively without justification. Start with rewrite predecessor, successor A, and take it from there. Okay, well, we're trying to prove that A equals B using the hypothesis that the successor of A equals the successor of B, which is, yeah, it's not letting us use this one because this one just proves it, but we're trying to go back and prove this since we never proved it. So, backwards arrow, the predecessor of the successor of A. This is the proof that the predecessor of the successor of n equals n. So pred successor A. Why? And that takes A equals B and turns it into the successor of A. What? What does the dot mean? Why is there a period? trying to prove that the successor of A equals the successor of B implies that A equals B. Start with, so N will become the predecessor of the successor of N. I don't know why there's a period. I don't know why it's... What do I do? I don't think that's what I do. I have no idea what I'm doing. I don't understand that. The predecessor of 0 is... I don't know what this means. Okay, I can get both sides like that. Then okay. Okay, that worked. So the successor of B's predecessor equals the successor of B's predecessor. And that proves that this... I don't know. I'm making progress through the game, but I don't feel like I'm really making progress on my understanding. Let's now prove Peano's other axiom, that successors can't be zero. So we're doing a lot of proving axioms here, which is interesting. Alright, we define a function is zero thus. Is 0, 0 true? Is 0 successor of n is false? Did it ever explain what that means? What the... Is this just implies? But the arrow was implies. We also create two lemmas, is 0, 0, and is 0 successor n. Is 0, 0 is a proof that is 0, 0 equals true. And this is the proof that is 0 successor a equals false. Let's use these lemmas to prove successor ne 0, Peano's last axiom. Actually, we have been using this before, but it's handy to have this opposite version too. Which can be proved in the same way. Note, you can cheat here by using 0 ne successor. But the point of this world is to show you how to prove results like that. If you can turn your goal into true, then the trivial tactic will solve it. The trivial tactic? Oh, that's new. Trivial tactic will solve the goal true. Okay. Start with intro h, remembering that x does not equal y is just notation for x equals y implies false. I just read a lot of words and I don't know what any of them mean. Oh, okay. Start with intro H, remembering that x does not equal y is just... Okay, it told me what to do, and I didn't even see that. We're going to change that false into true. Start by changing it into is 0 successor A by executing rewrite backwards is 0 successor A. It really tells you what to do a lot more in these extra worlds, right? In the main world, tutorial world, addition world, multiplication world, and power world, the main game with the final boss, it doesn't tell you what to do, which is like harder in some ways, but also almost easier because you have to actually figure it out. Whereas in this, it just keeps telling me what to do, and then I get to the final level of the world, and I have no idea what I'm doing, because all I did was follow the instructions, and I never understood what I was doing. But okay, I guess we'll rewrite backwards arrow is 0 successor A. Oh, is 0 successor, and apply that to A. And this is the proof that this is false. We're going to turn false, which is this, into the successor A by going backwards through it. See if you can take it from here. Look at the new lemmas and tactic available on the right. The successor of A equals 0. But that can't be true. Successor of A dot is 0. Trivial? We'll solve the goal true. That's it. We totally just solved a math problem, and I totally understood how and why. What? Here we begin to develop an algorithm which, given two natural numbers, a and b, returns the answer to does a equal b. I'm going to be done for tonight. My brain is fried. See you tomorrow.